Hello there, Mr. Sutton here, bringing you the Algebra 2 Chapter 9 quiz review solutions on data analysis and statistics. For this problem, we're told a data set has a normal distribution with a mean of 2790 grams and a standard deviation of 150 grams. A value from the data set's randomly chosen. We want the probability that the value is 2870 grams or less. Since we're talking a normal distribution, and these numbers are a little bit crazy, I think the z-score formula would help us out here. So that's z equals x minus mu all over sigma. So the z-score again tells you how many standard deviations away from the center you are. X is your specific value that you're being given here, the member of the set. Mu, that is your population mean right here, this 2790, and sigma is your standard deviation of 150. So we have 2870 minus mu, that's this 2790, all over the sigma, the standard deviation of 150. And let's see what that comes out to. So make a fraction. We've got 2870 minus 2790 all over 150. So this is roughly 0.533. Now we do need to be careful because the z-score is not the actual probability that they're looking for. In order to get the probability, we need to actually plug this into our binomial distribution function. So let me go back here, and in order to do this, I'll make a new entry, and we need to do normal dist, and then do 0 parentheses 0, 1. This essentially gives us the the standard normal distribution that has a mean of 0 and a standard deviation of 1. That's what all of that means. And then we do dot CDF, which is going to give us basically the percentage, the probability. And then let's actually plug in this 0.533, so 0.533 out to as many decimals as you want to go. And this is going to come out to roughly, they said 0.703. So 0.703 then, that's the probability that a randomly chosen value in this normal distribution is going to be less than or equal to 2870. For this problem, they say in a survey of 500 U.S. teenagers, 61% say they are planning to watch the next Marvel movie. Is this a parameter or a statistic? So remember that a parameter is a piece of information about the entire population that you're talking about, whereas a statistic deals only with a sample of that population. So we're talking about a survey of 500 U.S. teenagers. So this is definitely a sample. The population would be all of the teenagers in the United States. There's definitely more than 500 of them. So because of that, because this is about a sample, this is a statistic, not a parameter. So a statistic because we only looked at the 500 U.S. teens, not all of the U.S. teens. On this problem, we have a coin maker claiming that a coin is fair, which is to say it does not favor heads or tails. You use technology to simulate 200 random samples of flipping a coin 50 times, and the histogram shows the results. You then flip the actual coin 50 times and get 37 heads. We want to know your sample proportion and what you should conclude about the claim that the coin is fair. So our proportion is just going to be 37 over 50. Which comes out to 0.74 if I'm not mistaken. So this is your own personal sample proportion. This is a simulation of basically doing this 200 times, and here's what the computer got, all the different proportions that the computer got when it did this. So in order to see if the claim is true or not, we have to compare our proportion to all of these proportions here and see how likely our proportion is based off of what we should have gotten if a coin were actually fair. If a coin were actually fair, then we should have gotten basically a 50-50. So looking here, here's a 50-50. This would be 0.50. Now 0.74, if we look in our frequency table here, our histogram, 0.74 is like all the way over here. There is zero frequency that this is going to happen randomly. So because this is a very low frequency, the claim that this is a fair coin is likely false. This is not likely to happen by chance. On this problem, they want us to identify the type of sample being described. So we have a student who wants to know how their peers will vote in an upcoming student election. They randomly select 3 homerooms and ask every student in those homerooms. So because we are randomly picking some groups and then asking everybody in the groups, this is an example of a cluster sampling process. Now the other ones, just to kind of review them, if you had a simple random sample, basically you'd be throwing everyone's name into a hat and just randomly picking a few and asking them. If you had a systematic sampling, you'd have a rule for picking people, like picking every 5th student in the student directory. Let's see here, a stratified sample would be if you took random students from all of the homerooms, but each homeroom had an equal chance of being chosen, and the students in individual homerooms had an equal chance. And then what are the other ones? Let's see here. We've also got the self-selected sample. That's where people volunteer to give you their input. And then the last one, I think, was the convenience sample, which would have been if you just like stood at the door of the school and asked the first few people who came in. The only other process I can think of would be a census, which would be basically asking everybody, but that's not really much of a sampling process. On this one, a scientist compares lifespans of individuals who eat a significantly high carbohydrate diet with those who eat a more balanced diet. Identify the method of data collection described in the situation. So we've got 4 big collection processes. One would be a simulation where you basically have a computer fake it a bunch of times and see what would have happened. So that doesn't really involve real life individuals at all. Another is going to be an observational study. That's where you basically just watch a bunch of people without directly doing anything to them. And another would be a survey where you ask people a bunch of questions about whatever you're interested in. And the last would be an experiment where you actually apply a treatment to groups of individuals, so you're actually doing something to them there. In this case, since we are comparing lifespans of individuals, we're not really doing anything to the individuals. We're not forcing any of them to eat high carb diets or more balanced diets or keto or anything in between. We're just watching them. So because of that, and it doesn't really mention that we're asking them anything, we're just kind of observing. So this looks like an observational study. For this problem, to test a new drug for treating an ailment, a pharmaceutical company divided 400 adult volunteers into 2 groups, an under 50 group and a 50 or older group. One group received the drug and one group received a placebo. After 1 month, the adults who took the drug were 52% less likely to experience symptoms, while those who took the placebo experienced no significant change. Is the study a randomized comparative experiment? Why or why not? So this one actually fails to be randomized on 2 counts. One of them is the fact that the groups that the pool of people that the drug company is choosing from were volunteers. So already you're not getting a random sampling of the general population. Also, we split the people into 2 groups that were very different. So we have an under 50 group and a 50 or older group. So whether or not this drug works, or these results, actually, the 52% less likely to experience symptoms, might have more to do with the age of the individuals rather than whether the drug works or not. So because of this, because they're self-selected groups and because they're assigned by age, not gender, age, for all these reasons, this is not a randomized comparative experiment. For this one, we have a survey of 567 adults in a city, and 50% said they rate the city as a good place to live. Give an interval that is likely to contain the exact percent of adults in the city who rate the city as a good place to live. So basically here, we need to figure out the margin of error, and then we need to add and subtract that from the original percentage of 50. Now to get the margin of error, since they've just given us the sample size and not the standard deviation or anything like that, we're just going to use our approximation formula, which is going to be 1 divided by the square root of n. So our margin of error is plus or minus 1 over radical n. In this case, that's plus or minus 1 over 567 square root. Let's calculate what that square root comes out to, what that fraction comes out to. So we have 1 divided by SQRT, square root, 567, and that comes out to, if we make this a percentage, this is, let's see, roughly 4.2%. So now we need to subtract 4.2% from 50 and add 4.2% to 50 in order to get our likely interval that they're asking for. So 50 minus 4.2, I believe that's 45.8%. And then the upper bound on our exact percentage should be 54.2%. So actually, this doesn't contain all of the possible exact values, but what this margin of error does tell us is that there's a 95% chance that the exact real percentage is between this range. For this problem, a randomized comparative experiment tests whether a mentoring program affects number of absences from school. The control group has 8 students, and the treatment group, which participates in the program, also has 8 students. And here's the results from this table. This is days absent from school for the control who didn't get the mentoring program and the treatment who did. So they want the experimental difference of the mean yields of the two groups. So basically we just need to find the mean of the treatment group, the mean of the control group, and then subtract the control group from the treatment group mean. So we don't need to use a list in Desmos to do this, but I'll just show you the list just because it's kind of cool. Good to review that ability there. So again, if you're going to make a list, it's a good idea to name it. So I'll use C for the control group, and I'll say C equals, and now I need brackets, and I just put in my values with commas. So we got 6, 8, 8, 8, 7, 9, 12, ooh, that's a lot, and 4. All right, so that's my control group. My treatment group I'll call T, and I'll do the same kind of deal with brackets. So 4, 4, 5, 2, 3, 6, 0, and 7. All right. So now let me go ahead and take the mean of the control group, and that comes out to 7.75. And now the mean of the treatment group is 3.875. So I just need to do 3.875 minus 7.75 in order to find this difference that they're asking for. And this little X bar thing is just talking about a sample mean. So let's go ahead then and do 3.875 minus 7.75 to get a final answer. And that's going to be negative 3.875, which is kind of interesting. So at least based on the results in this table, it looks like our mentoring program is reducing the number of absences by roughly 4, which, hey, maybe it's worth it.